Hello, in this video we are going to take a look at 3 AP questions that all involve a given table of values, and the question asks you to analyze it in different ways. In this question we have, let f be a polynomial function with the values of f prime of x given in the table above. Which of the following could be true for x between -2 and 6? Alright, so that chart gives us the values of the derivative, but you notice in all the choices, they all are asking something about the original graph. If it's concave up, has 2 points of inflection, increasing, no critical points, has at least 2 relative extrema. What do we know about those statements in relation to the first derivative? If it's concave up, that means the derivative is increasing. If it has 2 points of inflection, well, points of inflection on the first derivative are max or min, okay, because that is where the slope would switch from increasing to decreasing. If f is increasing, that means the first derivative is always positive. If it has no critical points, that means there are no x-intercepts on the first derivative. If it has at least 2 relative extrema, well, that means there are 2 x-intercepts on the graph, at least 2 x-intercepts. So I'm looking for all those different things on the graph of the first derivative. Since they are so easy to see on the graph of the first derivative, I would recommend sketching a quick first derivative based on the given values. So we'll do that here. -2, 3, we're there, 0, 1, and it can be just an estimate here. That's all we need. 3, 4, 5, 7, a little bit higher, and then 6, 5, back down low. Now, if I want to connect these in the most obvious way, we're going to go like this. Is it increasing? Is that graph of first derivative increasing? We see that it does decrease for portions, so it's not always concave up. 2 points of inflection. Does it have 2 points of inflection? Does it have 2 max or mins? It does. It has one right here and one over here. So that's a possibility. Is the derivative always positive? It does appear to be that way, but here is where this problem gets tricky, because you got to think of every scenario of what it could be. Is there a way to draw this graph so that it's not always positive? There kind of is. If I sketch it like this, and right here, if it just keeps going down and then pops back up to hit this point, there is a way to make it negative, which means at that point it would be decreasing. So that is not always true. Has no critical points. Well, how I drew it in green, it had no critical points because there's no x-intercepts. However, again, when I tried that red drawing, I all of a sudden had 2 critical points. So that's an issue. It might have critical points. Has at least 2 relative extrema. In this case, with the red, it does have 2 extrema because it has 2 x-intercepts. But when I drew it originally in the green, it had no extrema because it had no x-intercepts. So we're left with the only feasible possibility being 2 points of inflection, and you see that still holds true even with the graph of the red. Okay, because when I'm going down, I have to come back up to hit that point at 3, 4. And I could try over here. I could say, okay, I go way down, but then I have to come back up to hit that 0, 1. Same thing here, because I have a point below and below on either sides of this. I'm going to have to go up and then down to hit the other point. So I'm going to have a max here. I'm going to have a minimum here, no matter how I try and draw this graph. Correct answer is B. The graph has to have at least 2 points of inflection because on the derivative, I have to have at least 2 max or mins. In this question, it says, if f prime of x is greater than 0, which means the function is increasing, for all real numbers x, and the integral from 4 to 7 of f of t dt is equal to 0, which of the following could be a table of values for the function f? So this means area under curve is equal to 0 on the interval from 4 to 7. But let's first focus on the fact that f prime of x is greater than 0. That means the function has to be increasing. That means as x increases, the y values also have to increase. That holds true for table A. That holds true for table B. That does not hold true for C because here it's increasing, but then it's decreasing from 6 to 3. D does not hold true. Those values are staying constant, neither increasing nor decreasing. So even though the integral of that would be 0, it would not be increasing, so it fails the first condition. E is also increasing. Okay, so we're down to A, B, and E. Now we have to focus on the fact that the area under the curve has to equal 0. That means when I go between 4 and 7, it has to be something that looks like this, where the area of this above the curve has to equal the area of this below the curve. When I take a look at table A, where 4 is negative 4, 5 is negative 3, and 7 is still 0, that's going to be a graph like that. Notice how that is always below the curve. Therefore, that is going to be a negative value. It is not going to equal 0. So not that. Looking at B, that starts at negative 4. It goes up to negative 2. And then it ends way up at 5, which looks a lot like that curve we had sketched out at the start. So that's a possibility. That could work. There could be an equal amount below the x-axis and above. But we better check E to make sure. For E, 4 starts at 0. It goes up to 4 and then continues up to 6. And what do you see there? It's all above the x-axis, which means it's always positive. It's not going to equal 0. So we're left with B being the only feasible option. Finally, the last question we're given. The table above gives the distance, s of t, in miles that a car has traveled at various times during a 6-hour trip. The graph of the function s is increasing in concave up. Okay, that basically is telling us nothing fishy happens in between these values. If it looks like it's increasing, it does in fact continue increasing. Based on the information, which of the following could be the velocity of the car at t equals 3? So the velocity at 3 is equal to what? Well, we know that the derivative of the position function is equal to the velocity. So this would be really easy if I was given the position function. I'd just find the derivative of it and then plug in 3. But I am not given the position function. I'm only given values of the position function. That means I must approximate the derivative. And we know that a great approximation of the derivative is a secant line, or an approximation of the tangent line is a secant line. That would be just your slope, s of b minus s of a over b minus a. The key here, though, is if I'm trying to estimate at 3, I want that to be in the middle of my endpoint, because I want to center that t equals 3 value that I'm trying to find. Because if I'm trying to find the slope at t equals 3, and I know the things around it, maybe 2 and 4, so I have the curve there. If I take the secant line with 3 centered on it, it's going to be a good approximation. If I try and do it using t equals 3, it might throw things off a little bit if I were to use maybe 3 and 4, for instance. But so long as I center that point I'm trying to estimate between, say, 2 and 4, things are going to be good. So when I do this approximation, I'm going to go s of 4 minus s of 2 over 4 minus 2. That is, just looking at the table, make sure you center that point of interest between the points you're using for the approximation. So you get 150 minus 55 over 4 minus 2. Which will give us 95 divided by 2, which will give us 47.5 miles per hour, which is pretty close to 49. So I'd say as an approximation, we can be confident in 49 being our approximation. So the takeaway there is if they give you the values of a position function and you want to estimate a derivative of velocity, just center the value you are trying to find between the 2 points you use for your approximation. I could even technically use 1 and 5 as my approximate values because 3 is still in the center of it, and that would still give me an okay approximation. However, you're better off using the closer values.